Today we're going to continue on with Unit 5.2, Mechanical Energy. So energy is the ability to do work. Okay, so last time we talked about work and what implies work is being done. Remember, it has to be a force applied across a certain distance. So when work is done, there is a transfer of energy. Okay. And sometimes we just have a change in energy or a transfer in energy. It depends on the types of energies that we're looking at. So there are two forms of mechanical energy. We have kinetic and potential. Okay, so to start off, we're going to talk about kinetic energy. So kinetic energy is the energy of an object due to its motion. So anything that is moving has a type of kinetic energy. Okay, so kinetic energy is measured in joules. Okay, we have that's equal to 1/2 the mass measured in kilograms times velocity squared, which is measured in meters per second. Okay, notice too we have another equation here where we have work is the change in kinetic energy. So we can kind of expand out this change of kinetic energy to be 1/2 mass times the final velocity squared minus 1/2 the mass of the initial velocity squared. Okay, so it's just the change in that kinetic energy going from final to initial. So for this first practice problem, what is the speed of a 0.145 kilogram baseball if its kinetic energy is 109 joules? So our equation was kinetic energy is equal to 1/2 mass times velocity squared. So they actually give us kinetic energy. Okay, they tell us the mass of the baseball. They both are in the correct units, so we just have to solve for velocity. So our kinetic energy, 109, is equal to 1/2 mass 0.145 times velocity squared. So I would divide both sides by the 1/2 times 0.145 and then take the square root of both sides. So let me go ahead and do that in my calculator. So I'm going to take 109 divided by 0.5 times 0.145. Then I'm going to take the square root of my answer. And I'm going to get that my velocity is, and I'm going to report 3 sig figs, so my velocity is 38.8 meters per second. Okay, for the next one, how much work is required to accelerate a 3-gram bullet from rest to a speed of 40 meters per second? Okay, so first off, they did give me the mass, but it is in grams, so I do have to convert that to kilograms. Okay, and then they gave me from rest, so 0 is my initial speed, and then my final speed is 40 meters per second. So we're trying to find work, so we're going to use that work is equal to a change in kinetic energy. This is going to be 0.003 kilograms. So just to kind of convert that, I moved my decimal over 3 places. So my work is equal to 1/2 my mass, 0.003, times my final velocity squared, so 40 squared, minus 1/2 0.003 times 0, because my initial velocity was at rest, so 0. Okay, so really this just kind of cancels out, so I'm left with the other side. So I'm going to take my 0.5 times 0.003 times my 40 squared, and I'm going to get 3 sig figs, so my work is 2.40 joules. The other type of energy was our potential energy. This is stored energy or energy of position. So we're going to talk about gravitational energy today. And then our next lesson will be on elastic potential energy. So gravitational potential energy, we use this as potential energy. We use U, and then the subscript kind of denotes what type of potential energy it is. So we use the G for gravitational. It's associated with the position of the object relative to the gravitational source. Okay, so for our equation, again, our potential energy is measured in joules, just like we saw with kinetic energy. We have the mass, which is in kilograms. We have G, which represents gravity, so 9.8 meters per second squared on Earth. Okay, and then we have our height, which is measured in meters. Okay, so here we have a situation where a ball was moved. Okay, it was lifted up to this height. This ball was rolled up the ramp to this height. Okay, and this ball worked its way up this staircase. Okay, but in each of these three situations, okay, the height is the same for all three. So all three have the same gravitational potential energy. Okay, so the path does not matter or does not change the potential energy, so the gravitational potential energy. Okay, so just because, for example, this third one has a longer path to get to this certain height, the gravitational potential energy only considers the height above the ground. Okay, so that shortest distance, the displacement basically from ground to its current height. All right, so let's do our first practice problem. A 25 Newton object is held 2.10 meters above the ground. What's the potential energy with respect to the ground? Okay, so if we look at our equation before, we saw we had our mass in kilograms and our gravitational pull, acceleration, and then our height. Okay, so for this problem, they gave us the height, okay, but then they gave us a weight. They told us that we had a 25.0 Newton object. Okay, but we know that when we're finding the weight of an object, we take its mass times gravity. Okay, so basically the 25 newtons is just the mg. So it kind of took out a step for us. So for the potential energy, we have our UG is equal to our weight, which is 25 newtons, times our height. We're going to report 3 sig figs. So 25 times my 2.1, I'm going to get 52.5 joules of potential energy with respect to the ground. Okay, for this next one, a 2.75 kilogram box is at the top of a frictionless incline as shown in the diagram. What's the potential energy with respect to the bottom of the incline? Okay, so they did tell us the mass of the object. Okay, we do know what gravity is. Okay, but for our height, we need to make sure and not get tricked. They gave us this distance up the ramp, but that is not the height from the ground level to where the box is sitting. So we need to calculate what this portion, okay, what this height here is. Okay, so if we look at our little triangle that was created, this side is opposite of our angle. So we're going to do our hypotenuse, so 10 times sine of 40. Okay, in order to find the distance there. So I'm going to go ahead and find the height. So 10 times sine of my angle 40 degrees. And I get 6.43 meters. Okay, so now I have the height, I have the mass of the box, so then I can plug in to the equation. So my gravitational potential energy is equal to my mass, so 2.75, times gravity, so 9.8, times the height, which is 6.43. 2.43. So 2.75 times 9.8 times 6.43. I'm going to report 3 sig figs, so 173 joules of potential energy. All right, for the last one, the bob of a pendulum has a mass of 2 kilograms and hangs 5 meters above the floor. The bob is pulled sideways so that it is 0.75 meters above the floor. What's the potential energy with respect to its equilibrium position? So they did tell us the mass, it is in kilograms. Okay, they told us 2 different heights. And the key thing here is we need to look at this final question. They want us to figure out what's the potential energy with respect to the equilibrium position. So its equilibrium position would be when it is hanging above the floor. So if we draw this out, okay, I have my pendulum, okay, and it is hanging from above, and it has a height here of 0.5 meters above the floor. Okay, but we're going to pull it to the side. So now it has a height of 0.75 meters above the floor. Okay, so the difference in position from its resting or equilibrium position here is 0.25 meters. Okay, so that is our height difference from that equilibrium position. So our gravitational potential energy is equal to the mass 2 times gravity times our height difference here, so 0.25 meters. So whenever I put this in my calculator, 2 times 9.8 times 0.25, I'm going to report 2 sig figs, so 4.9 joules of potential energy.